Lesson 5.7, page number 413, square roots and the Pythagorean theorem. Fun word, Pythagorean. What we're going to do in this lesson is we're going to get into to some of you, maybe some really new stuff. To others, it may be some stuff that you've done, but it scared you to death and you ran from it. Or maybe you just didn't get it. Maybe some of you did get it, and this is going to be a real easy section for you. That would be great if that happened with all of you. So anyway, we'll take it slow here and do what we can to make it as simple as possible for you. When we're talking about like opposites, opposite operations, the opposite we've done of multiplication was division, addition was subtraction, and vice versa. Now we're getting into where we're working with exponents. So we've got 3 squared equals 9. Okay? So when you have this 2 up here, that means we're going to take 3 times itself twice, and that gives us 9. Okay? So this symbol up here is an exponent symbol, and what that means is you take this number and multiply it by itself that many times. And you know that it's not 3 times 2, it's 3 times itself twice. Well, square root is kind of the opposite. A square root says, given this number 9, what was it I had to multiply it by itself twice to get this 9? So what number did I have to multiply by itself twice to get 9? Okay? So the square root of 9 is 3. The square root, square. 2 is squared. 3 squared is 9. The square root of 9 is this number here, the base that we started with. And so there's a symbol that when I'm asking for the square root of 9, it looks like this. It's kind of a sloppy one. Actually, it's a little tiny v, and it goes up, and then the number is placed inside of it. And that means the square root of 9. What number times itself gives me 9? Gives me that number that's inside of there. So that's what a square root is. Now it's getting used to using them on a regular basis. So let's go to page 414. Example 1. Let's just get into it with both feet. 7 square root of 64. Now there is no symbol, there's no operator in here telling you addition, subtraction, multiplication, or division. It's just nothing. That being the case, if there's nothing between the number and the square root of a number, it always means multiply. So this is kind of like a parenthesis. It's a symbol, so you don't have to write the multiplication sign. If you do, it's okay, but this is the common way of doing it. So what this is saying is we're going to take 7 times the square root of a number in here. In this case, it's 64. So you're always going to do the square root first, or they call this a radical. We're going to do that first and then multiply that answer times 7. So what number, if we multiply it by itself twice, is going to give me 64? Well, 8, because 8 times 8 is 64. And this is another thing that's very helpful. If you know your multiplication tables up to 10, or even better yet, up to 12, you will get all the square roots that you're going to need. So for example, the square root of 100. What did I have to multiply by itself to get 100? 10. Do the same with 81, which is 9, because 9 times 9 is 81. 64 here is 8. So if you know your multiplication tables, you'll know what number times itself is going to give me this, and you'll be able to just write it down rather than really try to figure it out. So actually that says 7 times 8 then when we're done, which is 56. So that's the multiplication of a number times a radical, or a square root. If we're adding, we've got the square root of 9 plus the square root of 16. If we have a square root sign over a number, you can't add these unless the number in the radical sign is the same number. You can't add them. If the letters, if you've got a variable under here, you can't add them unless they're the same. So we can't do anything with this. But we can simplify it and then maybe do something with it. Square root of 9, what is that? It's 3. Square root of 16, 4. Now we don't have radical signs anymore, and we can actually add these and get 7 for an answer. So as long as we can take the radical signs off, we can treat them like anything else and be done. So try to simplify what's in the radical sign first, and then see if you can combine. Alright, there's kind of a weird one, a square root of a fraction. Whenever you have a square root of a fraction, that means the same thing as the square root of the top number over the square root of the bottom number. So the square root of 25 is 5. 5 times 5 is 25. Square root of 81 is 9. And we get 5 over 9. And we're done. Alright, we're going to skip example number 4. It's just like we did for the most part of example 1. Example number 5 is basically the same as example 2, only we're subtracting instead of adding. So find the square root of 100, which is 10. Subtract the square root of 36, which is 6, and you just have 10 minus 6. Example 6 is the same as example 3. Which brings us to example 7. Give a decimal approximation for the expression 5 square root of 12. This is where your handy-dandy calculator comes in to play here. I expect you to be able to use it here on these particular problems. So up to this point we've done everything by hand. What we're saying here is it says give the decimal approximation. For the most part, the numbers that we deal with radical signs, there is not an exact number. 3 times 3 is 9, so we know the square root of 9 is 3. And we know the square root of 16 is 4, but there's no whole number between 3 and 4. And 12 is between 9 and 16. So somewhere we've got to figure out what number the square root of 12 is, and we know it's somewhere between 3 and 4. Well, there's no whole number between 3 and 4, so it's going to have to be a decimal. So because of that, most of these radicals you're going to deal with, they don't end. When you start dividing, they divide and go point, all the way into infinity, and there's no end to them. So that's why we're saying an approximation, because we really don't know exactly what that decimal is. And if you look in the middle of page 415, example 7, they give you the square root of 12. They say it's 3.4641016, and it even goes on and on and on past that. So they're just asking for an approximation, and it says to the nearest 10,000s. So let's just go ahead and multiply that 5 times that huge number, and we get 17.320,508, and again it goes on and on and on. But since they only were approximating to the nearest 10,000, 10, 100,000, 10,000. So this is my 10,000. I don't really need to go on and on and on. I'm just going to round this. Well, if I look here, my number to the right of my 5 is less than 5, so this isn't going to change. If it was greater than 5, or 5 or greater, it would change to a 6. This being the case, it just goes away. And there's our answer right there to the nearest 10,000s. And they give you a few more there, examples 8 and 9, which brings us up to a new concept possibly on page 416 called the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared. And what that means is when we have a triangle, any triangle at all, as long as one of the angles is a 90-degree angle called a right triangle, if we know the length of A and the length of B and the length of C, or if we know any combination of those, we can find out what the other side is. So for example, if you look at example 10 on page 416, they give you one that we'll do in just a minute. I'm going to turn the video off and we'll go into 5.7b, and then also on 5.7b we will do some of the problems.